Most of us view problem solving as a simple geometric proposition, a straight line drawn from point A, the obstacle, directly to point B, the solution. But cognitive science shows that in practice, analytical intelligence rarely operates on a straight line. The process is a dense, non-linear web of cognitive traffic. True analytical intelligence relies on the conscious, structured direction of mental processes required to navigate from that initial problem state through a maze of obstacles to a thoughtful solution. Yet modern education and corporate management systems operate on a massive blind spot. They almost exclusively test and reward the final output. We hand out a grade or a bonus based purely on the solution presented at the end. When we look at history's most catastrophic failures in business and geopolitics, they rarely happen because the people involved lacked raw intelligence or data. These massive systemic failures stem from microcognitive breakdowns occurring in the intermediate processing steps, long before anyone even attempts to finalize a solution. To map these breakdowns, cognitive psychologist Robert Sternberg established a consensus model identifying the higher-order processes used in problem solving. This model treats problem solving as an architecture of isolatable nodes, ranging from identifying the problem to evaluating solutions. The order is not fixed. Individuals regularly reverse direction or bypass nodes depending on the specific demands of the problem. By explicitly isolating, deconstructing, and training these specific cognitive nodes, instructional designers can step past the final output and engineer the foundational architecture of analytical thought. The cycle begins with identification. A solver must recognize a problem exists and accurately define its parameters. An accurate definition is the absolute prerequisite for any viable solution. Consider the Nixon administration during the Watergate crisis in 1972. The administration made a fatal cognitive error early in the cycle. They defined the crisis as a public relations problem requiring a cover-up, while the reality was a legal problem requiring absolute transparency. By misidentifying the root state, their chosen solution guaranteed their downfall. Similarly, for years, the U.S. auto industry struggled to sell cars in Japan. Detroit defined the problem as unfair trade restrictions. The actual problem was that Japan drives on the left side of the road, and Detroit was exporting cars with the steering wheel on the left side of the cabin. In academic settings, we frequently bypass this node entirely. We hand students predefined essay topics and specific equations to solve, doing the identification work for them. Teachers must stop generating the topics. We need to indirectly test intelligence by evaluating a student's ability to examine a broad subject and define a narrow, sensible question entirely on their own. If the initial problem is misidentified, every subsequent cognitive resource is wasted trying to solve the wrong equation. Once a problem is defined, solvers must decide how to partition finite limits on time, effort, and personnel. Executive history is full of resource allocation failures. President Jimmy Carter struggled with this note by refusing to delegate authority, allocating his own time to trivial tasks while delaying high-level decisions. Conversely, President Ronald Reagan over-delegated, allocating insufficient personal oversight to subordinates who then executed tasks poorly. In the classroom, a 1987 study by Wagner and Sternberg on reading comprehension demonstrates how standard testing fails to measure the specific skill. The study found that average and poor readers allocate their time uniformly across all texts. They apply the same unvarying effort to every paragraph, showing no systemic strategy. This dual heat map visualization illustrates the difference. On the left, uniform reading effort applies a solid block of attention over a page. On the right, expert readers dynamically partition their time, focusing heavily on highly relevant paragraphs based entirely on whether they anticipate a detailed multiple-choice test or a broad essay prompt. Instructional designers must force students to explicitly divide their time before beginning a test or lab project, allowing educators to assess the logic of that resource division before the work even begins. Standard reading and intelligence tests often measure a student's unprompted ability to allocate these resources, instead of their raw comprehension of the material. The third node requires the solver to structure their raw data. Expert problem solvers dedicate significantly more time early in the cycle to organizing information, which drastically reduces the time needed to execute the solution later. When information is structured poorly, the results escalate quickly. Take the geopolitical standoff between India and Pakistan. Newspapers and politicians in each nation have frequently portrayed the other's government through a framework of absolute distrust. When rival governments represent each other as fundamentally dishonest, meaningful negotiation becomes logically impossible based on that flawed data structure. Inside the classroom, students are too often asked to simply calculate a math problem or write a final paper without ever proving how they structured their thoughts. Educators should grade the intermediate deliverables. Assess a student's ability to represent verbal information as an algebraic equation, or require spatial diagrams and concept outlines before a single word of a draft is written. If the raw data is organized ineffectively, the final cognitive output will be inherently corrupted, regardless of the effort applied in the final stages. The fourth node requires the solver to formulate a strategy. This is the conscious sequencing of processes, deciding the exact order in which to act upon the newly organized information. A severe sequencing error nearly ended one of the largest tech companies in the world during the early operating system wars between IBM and Apple. IBM opted for an open system that third parties could copy, resulting in massive software development and market dominance. Apple chose to zealously guard a proprietary system. Because of this sequence of decisions, software development for Apple stalled, and their market share rapidly declined. It took a complete strategic realignment and hardware overhaul, marked by the introduction of the iMac G3, to recover from that original misguided strategy. Classrooms must prioritize reflective problem-solving over impulsive execution. Teachers can force students to solicit peer feedback and explicitly defend the sequence of their operations before they are allowed to execute an assignment. Strategy is the necessary bridge between organized information and successful execution. Without a vetted sequence, action is just wasted energy. The final active execution node is monitoring problem-solving strategies. This requires ongoing verification that current actions are actually moving the solver closer to the desired solution. In 2002, the CIA was tasked with determining the status of weapons of mass destruction in Iraq. The agency suffered a severe monitoring lapse. They failed to comprehensively track and update their internal models with newly available, well-hidden intelligence until 2004, long after the U.S. invasion had already occurred. This mirrors a common student behavior, executing a task blindly and handing in only the final piece of work, without ever stopping to check if the strategy was working during the process. Institutions must mandate successive drafts and require students to provide self-audits regarding how their work is progressing against their initial plan. A strategy is only a hypothesis. Without rigorous, dynamic monitoring, an organization or an individual will blindly execute a failed plan to completion. Problem-solving is never a linear sprint. It's a continuous mathematical reality that repeats indefinitely. Buying a car solves an immediate transit problem, but inevitably introduces new financial problems. The solution instantly becomes the new problem state, feeding right back into the cycle. Because today's solution dictates tomorrow's problem, possessing a robust, adaptable cognitive cycle is far more valuable than arriving at any single right answer. For educational professionals and instructional designers, the mandate is clear. To foster successful analytical intelligence, the focus of the classroom must shift away from the final product. Educators must actively prompt students using the specific verbs of this cognitive architecture: identify, allocate, represent, strategize, and monitor. Engineering these individual nodes directly into our curricula provides students with a permanent upgrade to their cognitive operating system, moving beyond the simple search for a right answer.